Tomita, who's going to talk about LES on HTC.
Thank you very much. And, my name is Hirofumi Tomita from Japan. My institute is RIKEN ICE. ICE means the Advanced Institute for Computational Science. And anyway, thank you very much for still staying here. The title of my talk is the Scale LES, strategic development of a large eddy simulation code suitable to the future HPC. So our institute is a new institute, and this institute research collaborates with computer science people. And Scale is one of the library combined with computer scientist technology and also meteorological technology. So today I will talk about the introduce this library strategy. Okay, this is the outline of my talk. So first I will talk about the motivation from a computational background and also from the meteorological background. And next, I will talk about, I will explain the detail of Scale library, purpose and goal. And after that, I will show you current development of LES code in the activity of Scale team, team Scale. One is the computational performance and the dry turbulent test case, and also the moist test case focused on the stratocumulus phenomenon. And finally, I will talk about the future plan and the summary. So there were two trends of HPC environment. One is the related to architecture of future HPC. And in Japan, you know, so now vector machine is changed to the massively scalar machine. And for example, Simulator 2 is consists of 160 vector machine, and now we are ready to run the K computer, which is 80,000 scalar processor. And the other trend is it is possibility to change the general purpose machine to a special purpose machine. So example is one good example is Anton in the biophysical field, and also grape, which is used to the molecular dynamics field. So we have to consider many things related to the computer architecture. One is the row of byte per flops ratio, and massive internode communication frequency, and also heterogeneous architecture related to the deep memory hierarchy or something like that. So question is here. So we need the reconstruction of model concept or not. And also we have to concern which the best or better system for weather climate application. And so one more I want to say, what can we say about architecture design to the computer science people? So So most concern issue is row byte per flops ratio. So dynamical core, especially based on the stencil calculation, maybe become fatal. So the model performance based on the stencil calculation may be limited by the memory bandwidth, you know. For example, we experienced in K computer already. So K computer has a relatively high BF ratio. For example, BF ratio is about 0.5. But we can get a performance efficiency about 66% or to the 20% for double precision. So if we estimate future HPC, something like 100 petaflops or 1 exaflops, BF ratio is lower and lower, maybe less than 0.1. So at that time, we can get just a few percent of a total performance. So this is a very crucial problem. So next, this is a background from a meteorological model development trend. So you know, shallow cumulus and stratocumulus is one of the key issue for climate model. You know, so LES is one of the vital tool. However, current LES in the meteorological field is not enough because hypothesis of LES is based on the dry homogeneous fluid dynamics. So in meteorological field, moist process inject the energy at the grid scale. So this hypothesis is already collapsed. And also, usually we use a high aspect ratio of horizontal grid and vertical grid, large aspect ratio. But this is also not acceptable because this theory based on the homogeneous fluid dynamics. So we have to resolve this problem. So our ultimate goal is global LES. So before this challenging subject, we have to do a basic study from the viewpoint of computational and computer science. Okay. So in our institute, we have some team which is named Team Scale. This is a transdisciplinary research team in our institute, and we co-design the application, library, and development environment for weather and climate research. And this activity going to the Scale library. So this is our concept of scale. So our general concept to get high performance in scale is a simpler method and faster calculation and also reasonable accuracy. And for latest issue, we don't pursue the flops. If we use a higher order scheme, we can get easily high flops. But this is owing to reusability of cache memory. But I think second order or fourth order is maybe enough, because physical parameterization is not converged. So that is a first order or less. Okay. So that is depend on the that physical parameterization depend on the grid resolution. So in this mean dynamical core. In dynamical core, the second order or fourth order is enough. This is my opinion, but this is a debatable point. I think so. And current technical issue is we focused on the time integration method, and we have many time integration method. One is a full explicit method, horizontal explicit and vertical explicit. And also HEVI, this is a usually used method, horizontal explicit and vertical implicit. And also third one is a full explicit. And we are now comparing the performance of these temporal scheme for the future high resolution run. So which is suitable for the LES scale simulation is one of our aim. And but full explicit method gives a reference solution maybe. So first we construct a full explicit version. And our final goal is, as I mentioned, we developed a library and middleware based on the knowledge through the development, and provide them to the community as open source. Yes, three-dimensional full implicit method. So scale LES is one of the codes generated by the scale library. And this is main model components. Dynamics is full compressed non-hydrostatic system. And cloud microphysics, now we implemented a double moment 6-water category that is developed by Seiki and Nakajima. And also, we will use a spectral beam model developed by Suzuki. And subgrid scale scheme is now we implement a smuggling type scheme. Okay. So why full explicit? So full explicit has no divergence damping. So no divergence damping filter is needed, you know, because no split of time delta t. And also maybe the memory load store maybe minimal. This is our expectation. And if aspect ratio of grid becomes a unity, usually used HEVI is no longer so meaningful, because aspect ratio is becomes unity. It is not needed to split of method. Horizontal and vertical. And also full explicit method maybe give different solution against the other temporal scheme. So first we decide to develop a full explicit scheme to get a different solution. And the other is other question is why fourth order of advection term is needed. And you know, so the second order advection term has implicitly Laplacian type diffusion term, which may be overlapped with Smagorinsky type diffusion. So if we use a Smagorinsky type turbulence model, fourth order is necessary. Fourth order advection is necessary. So we employ the fourth order for advection term. So current target is now a K-computer system. And this is a specification of a K-computer. And the CPU is Fujitsu Spark 64. That is peak performance is 128 gigaflops. And each node, each CPU has 8 cores. And total nodes is over 80 kilo nodes. And interconnect is 6D mesh torus network. And the total memory is 1 petabyte. And so one for each node, BF ratio 0.5. Okay. So this is program strategy. So we use language. So Fortran 9023. It is easy to get the higher computer efficiency than C compiler. And the other, we use a C because C is very flexible for system software programming. Okay. And data array order is K, I, J, so Z, X, Y. And so most inner loop is vertical. Okay. 2 minutes? Okay. So to get the first communication, if the order of this IJK is used, additional overhead occurs. So, okay. And this is a remedy of deep memory hierarchy, but this is somewhat complicated. I skip here. Anyway, I/O problem is a big problem. So you know, so-called big data problem. So number of files and the total size increasing more and more in the future. So reduction of data is needed, and currently we use HD file with zip compression in the model. Okay, this is a computation performance of as a first preliminary result, and this show the control case and RDM case. RDM case is we use a remote direct memory access for communication part. So we can see communication part is about 50% in MPI case, and that less than so in RDM case it less than to 5 minutes, so 3 times faster. Okay, and this is weak scaling results, and we can get perfect scaling over about 20 kilo CPU. And if we use RDM version, so this can enhance communication speed 3 times, something like this. So, so we show the preliminary result a little bit. So first, we try to dry tolerance test case. This is a configuration, and so aspect ratio becomes large the ABS can produce the same result or not. This is current our concern issue. Okay, this is control RAM. And this is a comparison of statistics. And so we configure the delta x, so aspect ratio of 1, 2, 5, 10. And we can see if we aspect ratio large, some zigzag noise appears in the turbulence heat flux, something like this. Okay, this is energy spectra, just aspect ratio, the case of aspect ratio of 1 and 5. It's okay. And now we aim to the so moist convection system. And now our target is here. So one is a very high resolution run for DICOM 2 R01 test case. And this is will be done by 5-meter cubic grid with a spectral beam method. And we can see, we can give one reference solution for database. Okay. The other is a very wide domain mesoscale ABS RAM. Okay, we have no time, so we skip here. So this is summary of my talk. So LES is a vital tool. However, we should overcome several issues. One is validation of the aspect ratio of grid. And usually, very large aspect ratio is used in the meteorological application, although the theory has assumption of homogeneous turbulence. So this is very, we have to resolve this problem. And treatment of moist process is one of the problem. So moist process injects the grid scale energy so that the energy cascade theory in the inertial subrange may be invalid in this case. And also hardware and software in HPC becomes changed now. So chip architecture, system software, and the program environment will be changed. So we should collaborate with computer scientists to build up the next generation HPC. And the scale library provides the environment for easy development of meteorological and climate model. And now scale activity is in the starting point. Okay. Thank you very much.
We have time for one question.
I have a question. You said in the beginning that that you're most concerned about the byte to flop ratio of the computers that are coming up. Now, that is of course true, but on the other hand, current computers also allow for interleaving communication with computation to much more extent than it was formerly possible. So if you could exploit that, could you kind of avoid the dilemma?
So, so you mean the infra network?
Yes.
Yeah.
Yes.
Yeah. One problem is byte per flops and also interconnect low speed. First, we have what we have to do is get the high performance in a node.
Yeah,
so
that's true.
In this sense, we have to do first to get the high performance in a node model.
Any other questions? Niels.
You had a statement where you said that in the context of bringing the vertical resolution similar to the horizontal resolution, the concept of heavy is no longer meaningful. But I would argue that, because at least from my experience of runs in direct numerical simulation and also LES, it seems that you get the qualitatively correct solution with less, relatively speaking, less vertical resolution if you have some form of implicit coupling of the variables. So if you go fully explicit, you need much higher resolution in order to achieve the same result. And so to some extent, this issue of the aspect ratio can be alleviated, at least from my experience, by implicit coupling of the dynamic prognostic variables.
Yeah. So first, I want to making a reference solution to other researcher group for DICOM test case. So implicit solver is vertical implicit solver is a very good choice. But maybe implicit solver, so it is possibility to reduce gravity wave or something like related wave if we use implicit solver. So we avoid this situation. So we first do full explicit in this case.